works for in the summer class I was teaching.
Yeah.
And the guy at Home Depot was like,
The only way I could get that total interference pattern
if light in itself.
is if there was some interference, right? So the only way I could get that interference pattern is if there was like an interference of something going from there and something going from there. Yet I am now at a limit where I cranked it up to just one photon at a time, and I'm still getting the interference pattern.
Which means that the photon is not interfering with itself.
Which means the photon is interfering with itself, right?
Right.
So even in the one photon particle limit, the photon still interferes with itself. And you know, so it still is a plane, it's some type of plane wave impinging on the wall and going through both slits at the same time. Alright? So this is funky. This is purely...
One photon and it can go through two slits.
Okay, and then here's the deal, is if you're finding, you go, what if I put in 3 slits? What if I put in 4 slits? What if I put in 5 slits? What if I put in 6 slits? What if I put in an infinity of slits?
Still goes through the wall.
So what does it mean about the single photon?
The infinity of slits would just give you the flat way
The
down.
infinity slits is everywhere, right? When I have 2 slits, it means the photon's going here and here. But now I have an infinity of slits, so what does it mean about the photon?
Plane wave.
And it's plane wave and it's everywhere, right?
Yeah.
Funky stuff. Alright? So it's not so much even saying that it's going through 1 slit or 2 slits, you know, it's kind of everywhere. Alright? Real quick, alright, because I want to finish this up. What?
What was the book question?
Yep.
Equation 1.18.
I'm not there yet. I'm not there. I really can't get there yet, okay?
Okay.
Okay. So here's the deal, is that if we're in the single particle limit, and I had to say, well, how can I estimate the probability of where my particle is going to go? How could I do that? What would the probability be proportional to? The intensity. So check this out. The probability is proportional to the intensity, because where the intensity is the highest, that's where the thing will go. Alright, and what's the intensity proportional to? Not the energy. Well, the energy, and the energy is proportional to the
electric field.
The electric field, right? So this is proportional to the total electric field squared. Okay? Now, if I add up probabilities, so if I look at the probability from minus infinity to plus infinity, right? What is the probability going to add up to? 1. It has to add up to 1, right? It's got to be somewhere in that field, so check this out. So how about this? The integral from x equals minus infinity to plus infinity of the total electric field squared dx has to equal 1. Okay? So, or I could go backwards. The integral from minus infinity to plus infinity, a d probability has to equal 1. So that's the integral of d probability. So for example, what's the integral of d elephants? Elephants. What's the integral of dx? It's x. So the integral of d elephants is a whole elephant. Alright? So the integral of a tiny bit of probability, an infinitesimal probability, has got to equal 1. I know the probability is related to the electric field. I know that I'm doing this from minus x to plus x, minus infinity to plus infinity x. So this identifies this quantity, this amount of stuff as a bit of probability. Alright, and it makes sense. If I come over here and look, E total squared dx is proportional to the area under the curve. The bigger that little Riemann sum, that little Riemann area is, the higher the probability of finding a particle there. Right? So that's a little bit of probability. What does that identify this as? So check this out. The units of this are, so let's look at this. So E total squared dx has to equal d probability. This is something times distance or length, right? So what do the units of E total squared have to be? Okay, so yeah, Matt's almost got it. The length on the bottom, but what about on the top? Probability. Right? Okay, so we identify E total squared as a probability density. Gesundheit. Alright, so I have just finished everything on Maxwell's equation, and this is where Schrödinger might have looked. Alright, I'm pretty sure he didn't do it this way. Alright, but this is an argument that I always give. Okay, so now here we go. Here's how we're going to go to Schrödinger's equation. Alright, and we're going to go for electrons. I have 2 minutes, right? We'll get there. All right, if instead of lasers I do this, I take an electron gun. I have an electron gun. It gives me electrons. All right, and I fire electrons at a double slit. Guess what happens on the other side over here?
Interference pattern.
You get an interference pattern. Bingo. You get the exact same interference pattern. You got to change the slit spacing and stuff like that.
So a different jump that matter of an electron has wave-like properties.
That's right. So now that's what we're going to do.
The Compton wave of an electron versus the wave.
You got to worry about the Broglie's wavelength to figure out the spacings and stuff like that. All right. So if over here you've got the same thing, right? Remember, for light as a particle, I associated a wave. I found a wave equation, and essentially the electric field is the wave function for light. All right. So if now I have an electron and the exact same thing is happening, maybe there's an electron wave function, maybe there's an electron wave equation, right, in here, just like there was the light wave equation. And the solution to the electron wave equation is going to be, it has to be, plane waves again. Because the electrons have the same interference pattern, right? And so the solution to the wave equation for the electrons, instead of calling E is already taken up. We use that for the electromagnetic field, right? So let's just call it psi. Psi 1 and psi 2. And instead of calling it, the electric field, why don't we call it the wave function? So the electric field for the Maxwell's equations could be called the electric field wave function, right? So let's call this the electron wave function. Everybody agree? Kind of? Mm-hmm. All right. And what is probability going to be proportional to? Well, instead of having the total electric field over here, right, we don't have the electric field function anymore. We have psi total. All right? And so over here, this is psi total. And over here, this is psi total. And over here, what is this? This is psi total. And And this is how you do quantum mechanics, all right? So the only thing I've left out is the wave equation that Schrodinger found. It looks like this. It looks like h times psi equals IH partial psi with respect to t, which comes out to be minus h bar squared over 2m del squared psi plus v of psi equals IH partial psi with respect to t.
So we still call it probability density, or would you call it something else?
No, probability density. But it's probability density not for the electric field wave, it's the probability density for the
Electron.
portion. That's it. Okay, so guys, I know this was complicated in details, but does it make a little sense? I mean, to make that connection? Dino's saying, yeah,
Well, that's a little bit.
a little bit.
Are we going to be deriving that?
Yeah, and so I'll derive this. All right? I'll derive that. Not today, I'll do that the next time.
What do you get from Maxwell's equations?
Yeah, do this.
But it seems like pretty much the same.
So that's what I want to hear you say. It's all the same thing.
Pretty easy.
Right? But think about what we've done is we have really slammed the electron into being a wave, just like the electromagnetic field. I mean, like a light. Right? And then we saw light can kind of act like a particle. Right? You got it down to the particle like in a minute. And then what we did is we took the electron and we said, well, it also is a particle, but let's see what it looks like as a wave. And so we got this wave-like stuff for it. So the goal of quantum mechanics, guys, is you draw a picture. It turns out that here's the scoop. This is the kinetic energy. This is the potential energy right there. So you draw a picture of a system. You look at the kinetic energy, and the kinetic energy never changes. This never changes problem to problem. The only thing that changes problem to problem is the potential. For example, if you're doing the potential of a hydrogen atom, we already talked about it. What's the potential of a hydrogen atom?
Negative 13.6 electron volts.
No, that's the energy. That's the total energy. The potential energy is minus K E squared over R. So you just plug that in. And then you solve for psi. Okay? When you have psi, what is psi? Psi is called the wave function. Right? And what can you do with the wave function? Well, when you square the wave function, right, you find out the probability density of where it is. Right? So that's a very grinding idea of what you do. And again, Mike, you want me to get this equation, I'll get this equation for you on Tuesday. All right? And that won't take long. All right? You have this equation. Your goal is to solve it. Hey, look, with Maxwell's equation, your goal was to solve it and then square it and then find out what the pattern looked like. Right? In quantum mechanics, your goal is to solve this wave function for the electron and then square it and find out what the probability density looks like.
How did the E to the IK, how did that squeeze in there? What was
The E to the IKX, that is the solution. So let's do this for homework. So for homework.
You make me look like a bad guy.
Yeah, no problem.
What's up with that?
No good.
Slide.
Okay, partial squared E dx squared equals mu 0 epsilon naught d squared E dt squared. Show that e to the I kx minus omega t equals a solution.
So what do you do? Just get back into this?
That's how I would do it, Alabama. If I want to see if something's a solution to an equation, I throw that something into the equation and I see if it works. All right, so here's what I want to say, Matt, is that I didn't go through how to solve for it. Like I didn't go through how you go through the steps to solve that differential equation.
Right.
What I did is I just gave you the answer. And so just giving you the answer to convince yourself that it is an answer take that answer and throw it back in,
Yeah.
and see if it works.
So basically that came from, okay, so it's just a